Good morning, dear colleagues. Today we are going to discuss first on the basic principles of low power digital design, but as we shall concentrate more on two different aspects. That means we know that low power design, why it has come to become prevalent with the advent of portable devices. Now, as far as the low-end portable devices are concerned, like say wristwatch or the like, we don't have the headache to maintain certain throughput. Okay, mostly it is low throughput, and if it is low throughput, it is easier to maintain low power. But with the as we progress more and say consider the handheld multimedia terminal. Nowadays, internet has come to make a deep aggression in our daily lives. So imagine that we have to do on that handheld multimedia terminal video display and capture, then audio reproduction and display broadcast, then other things like say handwriting recognition, then voice recognition. Different tasks more and more are accommodated in a single terminal, and that calls for lot of computations as well as relatively high throughput, and high throughput is always accompanied by higher power supply. So lot of battery power is required, but as we know that there is a premium on the battery power. Okay, so we have to see how this contradictory requirement, namely high throughput and low power, apparently are very much contradictory. So how certain things like architecture can be tailored or fine-tuned to meet the constraint of reasonably high throughput as well as low power. So for that, what we do, so this is a topic we'll mostly there are several aspects like to ensure low power operation of electronic circuits while obtaining reasonably high throughput. The first technique, strategy that we shall take is regarding the voltage scaling approach. We know that the dominant component of power dissipation depends quadratically on the voltage, and yet how it can be downscaled but without violating the reasonably high throughput goal. And secondly, although it is accompanying the first one, we know that basically the power if you recall the expression of the power supply, it equals the product of the switched capacitance, the square of the power supply, and the frequency of operation. Okay, so both capacitance as well as power supply are closely involved in the expression of power. So we shall study first about the voltage scaling strategy, and then come to this, as well as we shall see how in an automated manner such things can be taken care of. Okay, that means without the user consciously taking measures to scale down voltage and switch capacitance. Now, coming to the first approach, voltage scaling approach, the dominant component of power consumption, as we have said, is proportional to supply of power supply voltage. So circuit elements, if you scale down the power, then the devices, the components are forced to operate with lower voltage, and consequently you reduce the drive current. So as you reduce the drive current, they are forced to operate in a slower manner, and that hampers the higher throughput. Okay, so we have to see that how the throughput can be managed even under comparatively lower supply voltage. The approaches to voltage scaling try to see we have to maintain reliability. That means let the device operate without causing some disorder, or the device may not be led to distraction. Okay, so different second order phenomena are there. We'll just briefly look into this, that can cause the device to malfunction to the extent that it can lead to eventual breakdown also. That we have to take care. So reliability has to be maintained while maintaining performance. And the speed energy feature that means we shall see that the product of energy and delay can be maintained, can be optimized, and thereby we can get an optimum voltage, and theoretically obtain optimum voltage. We can slightly go past that, that means exceed the voltage, but without causing much harm. Okay, and also effect of scaling the threshold voltage on power supply voltage. There is also a trade-off. How much we can bring down the threshold voltage and power supply simultaneously, but at the same time do not allow the leakage power to go above our hand, and also the switching power should be kept low, because as we shall see, the switching power and leakage power can be oppositely affected by the tuning of threshold voltage. We shall see through example. And finally, architecture driven voltage scaling. That means the architecture has to be slightly modified in order to meet the higher throughput. Now, as far as the first thing, reliability driven voltage scaling is concerned, we know that mostly this constant voltage scaling is very much prevalent, because although tremendous progress is taking place, but whatever the designers have done even 20 years back or 25 years back, we cannot totally throw them away. That will take a huge amount of man-hour and cost. So we have to think of design reuse. Now, as far as design reuse concerned, that means that it is better that certain different components are there, like the input-output drivers. Okay, the internal elements which are performing the actual logic computation, they can be changed with the advent of CMOS and scaling down of the CMOS. You can change the power supply, but the input-output voltage drivers, okay, they play an important role while you connect subsystems. So that means constant voltage scaling is thereby very important. This is very much in vogue. Okay. Now, this popular constant voltage scaling, however, is accompanied by the increase of electric field, because as we know from our basic school day knowledge that dV/dx equal to E. So electric field equals what you get by dividing voltage by the width. Okay. So as the voltage comes down, as the voltage is maintained constant and the dimensions, the different dimensions are scaling down, that means the length, breadth and width. So consequently the field increases, and the high field actually plays havoc with the device operations. It can lead to lower transconductance. Then particularly more important is the development of hot carriers. These hot carriers can lead to eventual breakdown if they are left unchecked. Okay, so that involves a lot of what you call random propagation of the electrons and holes carriers. Okay, and heating effect, all these are unavoidable if you apply constant voltage scaling and the field is allowed to increase. So the device degrades with time and finally it can break down. There is a certain possibility. Now, as a corrective measure, or you can say to prevent the electric field from leading to ultimate destruction, what has been done is that a lightly doped region has been sandwiched between this the heavily doped source and drain islands and the channel. We are taking into account enhancement mode device, so this channel is without any carriers. Okay, primarily when the gate voltage is below the threshold voltage. So that means between the channel and the N plus heavily doped region, a lightly doped N minus region has been brought in. This actually tends to lower the electric field, particularly near the drain region, because the electric field exerts influence mostly towards the drain side. But this is also there to get some extra benefit. So this N minus lightly doped region, and from that the LDD name has come, it reduces the peak electric field and thereby improving the reliability. Improving the reliability means that it particularly takes care of reducing the generation of hot carriers. Okay, electric field, if it is allowed to be allowed to remain at a high magnitude, it will definitely lead to the generation of hot carriers and they will randomly move in the channel. Of course, the current field can rise unchecked and heating effect can take place. Okay, so to reduce that, the lightly doped drain plays a very good effect. But the main problem is that the trade-off is that the series resistance of the drain increases. Okay, and thereby what happens is that the gain suffers. Although if you allow this mouse device to operate in the analog domain, mostly it will be in saturation, and that calls for steady generation of current. Okay, so if the current is decreased, the gain cannot be obtained, and so that performance can decrease. So always we have to think of a trade-off between the performance and reliability. In every effort of us, we shall see that the trade-off is unavoidable. Next we come to this energy delay minimum based scaling. Let me write a very simple expression and see how the this energy delay product can be minimized. Okay, so suppose we write the simple, say, energy multiplied by delay. Okay, so energy means it is power multiplied by delay. Again, the delay is coming. Now, power involves what? Power involves, as you know, CV. We are writing the C to be the switched capacitance, the output capacitance, or those capacitances which are involved in the switching. Different components of capacitance are there, but we are taking into consideration that capacitance which is particularly involved in the switching operations. And the power supply, so square is involved, and the frequency of operation, let us say. And when we talk about the delay, delay is also inversely proportional to the frequency. Okay, these two can come or not, it doesn't matter. And when you talk about again delay, now we play, what we do is that assume that the device is mostly operated in saturation. So that means the current is constant. Now, very simply, see, current multiplied by delay, okay, is what? This simple equation, charge. And so TD can be written as C VDD divided by the current. Now, as we mostly consider the deep submicron devices, okay, as you know that as opposed to the conventional devices where the current is quadratically varying with the voltage, in a short channel device or deep submicron device, the current, this current, say saturation current mostly we are involved, it varies inversely, it varies almost directly with the voltage. Okay, so that means we have something related to the width of the device, length of the device, and the gate capacitance per unit area. Let me write simply as a constant K. So K multiplied by the overdrive voltage, that means VDD minus VT. Okay, so essentially what we have got, it is C VDD divided by some constant multiplied by this overdrive voltage, okay, VDD minus VT. So that means we can write it as, say, some constant K C square and VDD Q, mind you. Okay, FF gets cancelled and simply VDD minus VT. Now what we do, this is the energy delay product, we write in short EDP. This is very much popular as a metric when we try to compare different designs. That means we say that energy delay product is a better metric rather than the power delay product when we try to compare different designs. Now energy delay product, we should always make an effort to optimize, that means minimize. So allow me to write, say, EDP in short as Z, as if we allow me to write, say, VDD as, say, dependent variable X. So dz dx, okay, we try to differentiate, and if you differentiate to 0, as if you operate on that, you will get that the optimum value of this, rather the power supply value, can be shown to be equal to 3 times the threshold voltage, okay, or 3 by 2, whatever, you can do it in correctly. So that means, so see that here this energy delay product can be minimized somewhere here. Okay, now so how much you can vary the power supply voltage? See, we have to make a trade-off here that the delay should not be allowed to go down very much so as to so that the throughput suffers, and at the same time the energy should not be spent much. Okay, so that we can suffer from some runaway problem and thereby consequent heating will come. So we have to make a compromise between the increased delay and the reduced energy. Okay, we have to maintain throughput. Remember that while low power design we are interested in, because we have to maintain a basic throughput and at the same time afford only limited power. Okay, so that means energy delay product, if you optimize as we have got in the expression that we have done, is that the power supply should be equal to 3 times Vt. Now, so that means we have to take some optimum value here. Whatever be the value, say that means this technology, say whatever technology, for a fixed technology, this EDP curve is shown. For different technology, the values will differ. Okay, and what we are showing normalized energy delay product also. Now, theoretically, we understand that somewhere in the neighborhood of 2 volt we have to take. But you can question, well, different applications will call on us to go for a bit higher voltage. Okay, and that may not be very harmful. Why? Slight rise in the energy can be there if we can accommodate that with sufficient cooling provision. It is the more important thing is that the throughput can be increased. Okay, so as there is a huge competition amongst the different smartphone manufacturers, okay, theoretically obtain the minimum VDD value, they may not keep. Nowadays, most of the times we see that sometimes the tab is getting heated because always the manufacturers are racing against each other to increase the throughput. Okay, because different functions are accommodated in a single wafer, on a single limited space. So people, although they do not express it, always go for a bit slightly higher VDD value. The energy will be going up. You see that the phone is getting heated, but to a limited extent. More important thing that they gain is that the delay is coming down. So throughput may take the better of the increasing energy. Okay, so thereby when we are discussing about VDD scaling, okay, it is dictated by the energy delay product, the theoretical minimum, but sometimes we tend to extend over the minimum. Now, after energy delay product, what we want to discuss is that voltage scaling using threshold voltage. Again, if you remember the expression that current directly varies with the VDD minus VT whole square, and when you take the time, throughput is our premium, so throughput is inversely proportional to VDD minus VT whole square. Now, if you reduce VDD as well as VT, you will see that the speed can remain constant. But if you decrease VDD, keeping VDD constant, then the delay can be increased. So you simultaneously bring down VDD and VT, then almost no loss in speed can be guaranteed. Okay, but what is the danger? If you that means, as for example, say you have got VTT equal to 1.5 volt, threshold voltage equal to 1 volt. If you plot the normalized throughput or even power delay product, whatever, you will see that similar performance will be obtained if you scale down VDD from 1.5 to say 0.9 volt, and VTD you scale down from say 1 volt to 0.5 volt. Okay, so that means you have to simultaneously bring down VDD and VT. But the danger is that if you scale down VT from 1 volt to 0.5 volt, the subthreshold current will rear its head. That means the subthreshold current increases with decrease in threshold voltage, and this can be an irritating static power dissipation. That means the device is not doing anything. The phone is silent, but some power dissipation, although in the range of nanowatt, will be constantly there. But you can question, only nanowatt is nothing. But remember that millions of transistors are there. Okay, so that means the sum total of all the devices from which this leakage power is drained out will be a significant component of the leakage or static power. Basically, the total power has got different components. The static power means nowadays the design is made in such a way that a direct path from the VDD rail to the ground rail may not be there. Always we make use of CMOS circuits. But sometimes, say for the voltage, the input-output buffer, sometimes bi-CMOS circuits are used. So although conscious effort is made that the power supply from direct current from power supply rail to ground rail is avoided, but sometimes due to rapid what you call the transition from on to off or vice versa, there is some direct path established. So static power, or more appropriately it's called short circuit power, is there. Short circuit power, leakage power, one component is subthreshold power, as well as the what you call reverse bias diodes are there, that is the parasitic diodes which are obtained in CMOS devices, as well as the dynamic power. More importantly, dynamic power actually consumes the lion's share of the total power, but this leakage power also maybe we have to consider. So consider a digital system in which the supply voltage is allowed to, we have taken one example, allowed to vary to keep the throughput fixed. Consider a ripple carry adder, say 16-bit ripple carry adder or whatever. We have to maintain a fixed throughput, say namely at 20 MHz clock rate. This is just an example. Supply voltage and switching power can be reduced while reducing the threshold voltage. However, reduction of threshold voltage and supply voltage is offset by an increased current. This is very important. Okay, so that means if you consider this curve, if you say along the abscissa you are plotting threshold voltage. As you are bringing down the threshold voltage, the danger of more and more leakage power will be there. See, on this direction it is increasing leakage power. We are showing by arrow the decreasing leakage power. So as we bring down the threshold voltage, more and more leakage power will be there. But what is its good role? The better thing is that the switching power gets decreased, because power is directly proportional to VDD minus BT whole square. So BT is coming down, that means less energy. Okay, so switching power is decreased, but the leakage power is increased. So again, this calls for a trade-off. That means how much switching power we have to bear, and at the same time leakage power also should not be much. That means basically there comes the question: optimum threshold voltage must trade off between adequate current drive at low supply voltage. Adequate current drive should be there so that the minimum acceptable throughput can be obtained, and also the subthreshold or leakage current can be adequately controlled, because subthreshold current, if it grows unchecked, it can lead to some heating. Okay, because of the millions of devices being controlled by a single power supply. Now we come to architecture driven voltage scaling. It is a major role of the architecture that it should compensate for reduced circuit speed. So speed cannot be allowed to go down. That means maintain a basic throughput, but you need to bring down power supply voltage. So how we can manage? Of course, the what is coming into your mind, you are right, that go for the parallelism and pipelining. Okay, we are discussing that. So for that also, let us take one example, that take a single processor implementation of some logic function, say the function of some input in. Let f sample be the rate at which the input samples are streamed through. That means the same rate at which the inputs are sampled. The sample voltage and this streaming rate is taken to be the same. And let the capacitance switched per cycle be this. Now see reference, it includes the, always there is the input register in which data is coming from the sampled input, and there is a computing element, the template, and then finally the output register. This will always be the basic structure. Okay, so we have to include the three components of the capacitance. The capacitance switched in the input register, C out register is the capacitance that is involved in the output register, and CF, it is a capacitance switch to implement the logic function itself. Okay, so in general, it's a simple expression. Power consumption of the data path involves this product of this square of the power supply voltage and the sampling frequency. Now, if we so here what we observe, the trading area for low power. So if you have a uniprocessor box, what we see is that as we subject the input register and the output register to the clock, we see that this input, the first input sample is valid for, let us say, 1 clock period, and in the subsequent clock period the output is coming. That means the latency is 1 clock period. Okay, similarly for the second component and so on. So what we see here is that the latency is 1 clock cycle and throughput can be maintained. But the thing is that if C ref is high or VDD is high, then the power spent will be too much. So what we are after is that can we bring down the power supply voltage in order to reduce the overall power, but at the same time maintain the throughput. So how it is possible? The easiest approach is that take into account the parallelism. That means what you do, replicate that boxes, that logic elements. So have say n numbers of them, but not. It will be better if the algorithm is such that we can do so. Consider the case of say matrix addition or the vector matrix multiplication. That means same operation is replicated. Then only you can have a duplication of the same logic elements. Okay. Not all the algorithms are tenable, are feasible, so that we can apply this philosophy. Okay. So on a case-to-case basis, if we do that, what we can do is that hardware duplication we resort to. N processing elements, each PE implements the same function f. They are allowed to compute in parallel. Input is broadcast to all the registers, but not at the same point of time. We cannot do it. Okay. We will discuss how. Gated clock are used to load each register every n cycle. So gated clock means, think of a ring counter. All of us have done it. So is that n-bit ring counter means that the clock for each output of different stages are valid only for a clock period, or a single clock period. So that means if you have say 4-bit n counter, 4-bit ring counter, and if you have got a say 4-stage parallel, stage 4 parallel circuit, then to each circuit you can put the gate clock, say Q1, Q2, Q3, Q4, right? That's what we are doing. So if you see here, is that say different elements are there. We are making use of the n number of elements, and here although we are showing this is a value of this, okay, but this clock 0 will get say this register, clock 1 will get this register, clock 2 will get, and so on. That means say if you see that, consider that we are doing some matrix addition. So the first row of the 2 incident matrix are what you call obtained from 2 parallel registers, say, okay, and are latched here. Similarly, next the second values will be obtained here. So there is a skewing of the clock. So this skewing of the clock, is obvious from this. So clock 0, clock 1. Okay. So that means, interestingly, although the input is valid here, the output is valid after n clock cycles. That means the latency has increased. The latency has increased from 1 to n, let us say. But what is a better way? What we gain by this? Gated clocks are used to load each register every n cycles. Output of the NPs is multiplexed and sent to an output register which operates at the throughput clock rate, mind you. But each register is clocked at m sample by n. So that means what we gain from here, see earlier if say one logic function block was kept, but it was having available a time say 1 nanosecond. T available time is 1 nanosecond. Now if you allow a parallel architecture consisting of 10 number of say similar identical blocks, then how much time is available now to each of the logic unit? Not 1 nanosecond, but 10 nanosecond. So an extended time period is granted to each of the logic function. So what we gain by that? If more time is available to perform some task, it means that the voltage can be brought down, is it not? Because the drive current is provided by the voltage. And if you require less drive current, because now the device can operate slowly. So parallelism, what it does is that each of the elements is allowed to operate slower. And if it can operate slower, it can afford to take lower amount of voltage, right? So that's what. That means a time available to compute the function is increased by a factor n over unipolar. It can be shown that roughly Vn is 1 by n. So that means earlier if you had required say just a example, say 5 volt, now we can operate with say 500 millivolt. Okay, and power improvement. This is also an approximation symbol I have used, because what is the reason? Reason is that see, we gain in terms of, we can bring down the power supply and power can be reduced, but not as much as we have shown theoretically. The reason is that the overhead has increased. The overhead means that this broadcasting capacitance is there. So many elements are there. Area has increased, right? Because power supply, on the downside, we have to spend more area. Then, I'm sorry, the overhead capacitance has increased, and also there is a multiplexer involved. So multiplexer has this capacitance overhead, the routing, the multiplexer tree, and the control. So this will account for some power, of course. But still, by adopting parallelism, we can reduce the power. At the same time, maintain throughput which is approximately as much as we had got using uniprocessor implementation. So here the benefit that we get is that lower voltage we can use and maintain similar throughput. Another approach is that pipelining. So what is pipelining? Is that, again, this is also case dependent. That means the matrix addition or this thing may not be applicable here. But if you think of some application, mostly we have to do in our whatever algorithm we try to implement. Say first we do multiplication operation, followed by exponentiation operation, followed by, say, modulus operation. So different applications, different computations are involved. Then we can think of a, say, 3-stage pipeline. One stage performs the multiplication, the second stage performs the exponentiation, the third stage performs the, say, modulus operation. Okay. So in that way, let us show by means of, that means we can split this into, say, if it is an n-stage pipelining, it calls for, the overhead is that we have to bring in different platform registers, n-1 platform registers, n-1 stages will be there, okay? And as before, the throughput can be maintained, but with lower. The thing is that n-1 registers are introduced. This reduces the critical path. As the critical path is reduced, that means the delay is reduced, that allows us to make use of lower voltage. Okay, so the Vn roughly, theoretically it is, say, 1 by n times the voltage, but again we have neglected the overhead. Overhead means in terms of the platform registers, that means so many registers we have to use. Okay, we cannot ignore them. That means these registers has to be fed power. So although power can be brought down, but not the rosy picture that we give, it is not that 1 by n times, okay, because the overhead capacitance due to these registers have to be considered. Now what we do, this is the second broad approach. That means we try to lower the switched capacitance. Okay, that means power equals the product of switched the capacitance that is going to be switched, square of the power supply, and the frequency of operation. Now this can be done on different levels, even starting from the technology. I think this is not visible. These are technology level. Okay, that means technology level means what? In terms of packaging, silicon on insulator, substrate packaging, the circuit logic, physical design, even the layout can be optimized for lower power. Okay, then architecture is definitely there. Concurrency, instruction set, selection, signal correlation is the thing that we shall lay stress on. In signal processing operations, if you can manipulate the temporal sequence of data in which we can introduce some signal correlation by applying redundancy, it will be helpful in terms of lowering power. Remember that overall objective is that power should be brought down, but the throughput should be maintained. Okay. And algorithm wise, again, it is also very important. If the algorithm we can parallelize, not all algorithms we can do, then we can think of some what you call rescheduling of the tasks so that lower power can be afforded. And at the system level, that means we can power down parts of the circuit or entire circuit like that. Now let us take it up in details. On the algorithm level, we have taken an example where for a video stream, a number of elements can be combined based on their correlation. So quantizing rather than a single element, why not quantize a group of elements? Basically, when we talk about vector quantization, the brute force basic quantization, that is a what you call unoptimized algorithm is such. This is a performance metric mean square error. Okay, is to compare input image with the code book entries. Let us assume a code book of size 256. Okay, and xj is the input vector. Now suppose this each input vector, we say that it consists of 16 samples, 16 pixels. Okay, so a group of 16 scalar elements will constitute a single vector. So where xj are the elements of the input vector, each made of the 16 pixels, and the Cij stands for the elements of code book. Assume a size of 256. So the distortion calculation, how much the input vector varies from each of the code book entries, is given by this equation. Now, how we can perform is that the vector quantization can be either full search or tree search in nature. Let us see one by one. In full search, which is a brute force method, we have to compare the input vector with each of the 256 entries. So how many calculations are there? Obviously 256 different distortions, and within that 256 distortions, you see that we have to bring the 16 memory accesses, because they are staying in the memory. Also the code books are there, code book entries, 256 comparisons will be there. So for each distortion calculation, 16 memory accesses to fetch the code word entries, 16 subtractions, 16 multiplications, and 15 additions. Also 255 comparisons. So a huge amount of operation will be called for. Okay, so that's what number of memory accesses, 256 code book entries, 16 multiplied by so many. Each memory access will cost us power. Okay, so and number of multiplications are these 16 multiplied by 256. Number of subtractions are this, and number of additions are this. So the power that will be consumed is quite sizable amount of power. Now, for vector quantization, it is possible to go for a limited number of comparisons. That means by tree search. So what is that? Let us show by means of a simple structure. That means basically the input vector, we think of a tree search. So at the leaf level, all the code book entries are there, and at any point of time, at any level, the input vector is compared with not more than 2 elements. And suppose it is obtained that the given input vector is closer to this left element rather than the right element, then in the remaining time of the search, the right part of the tree will never be traversed. Okay, so that means the number of comparisons are reduced. Also, the number of levels that one has to go down varies logarithmically. So if you have got 256 total entries, okay, so total number of levels that you have to go through is log 256 to the base 2, that means 8. So 8 levels will be involved, and also see that how the number of operations are coming down. Okay, so instead of the number of memory accesses will be definitely there, but number of multiplications will be less by a factor of 16. This will be also less by a factor of 16, and so on. So that means basically 2 into log 2 8. Why? Because at each step, at each level, the comparison that will be required between this and this. So 2 comparisons at each level, and there are 8 levels. So 2 multiplied by 8, 16 distortion calculations will be called for. Earlier, 256 distortion calculations were called for. So this tree structured vector quantization, of course, there is some degradation of performance. That means the fully correct value we cannot get as we get in the brute force full search. That is due to the constraint on the search. But this is not very perceptible, this is not very noticeable, and power reduction is significant. That is the gain we have obtained. Okay, power reduction is definitely very tangible, but number of comparisons is there and some degradation will be there. Next, what we go, So what we do is that is choice of data representation. Now when we talk about that, in general, if you have say a chip is sending data to another chip, normally what we do is suppose an n bit data is shown is sent to, that means you have got a sender. If you have got a sender, say an n bit data is being sent, say x0, x1 and say xn minus 1. Now if you send it directly to the receiver, then power may not be at all cannot be saved. Rather what we do, we go for some redundancy, or rather what we talk about is that the coding. As the sender communicates with the receiver, coding what is done. For one thing, depending on application, if we think of say encryption, okay, there the scrambling is done and correlation we try to avoid. We try to decorrelate the successive elements, so that it is very difficult to decipher. On the other hand, if you want to reduce the power, sometimes signal correlation can be artificially introduced. Okay, so what we see is that, say from for n bit word, you can have a total of say 2 to the power n, this many elements. Now this is passing through a decoder on the receiver end, and you finally get the n bit word, okay, on the receiver. Now the question is that if redundancy has to be brought in, that means each of the input word can have 2 to the power n bit combinations or patterns possible. Okay. Now these combinations, if you go for 1-to-1 mapping, okay, 1-to-1 mapping means that finally you get here say let us say m equal to say, so here you get m number of bits out of the encoder. Okay, so here I have written 2 to the power n minus, this is a particular case, say call for am, okay, say m bits. That means, and normally m is much larger compared to n. That means redundancy we call for when you try to introduce redundancy. Okay. Now if you go for 1-to-1 mapping, that means for each n bit number there is a unique m bit number. So that means 2 to the power m minus 2 to the power n, these many combinations are never going to be used. Rather than that, if you go for 1-to-many mapping, then the encoder and decoder has to have memory. Okay, if you get 1-to-1 mapping, there is no need of introducing memory within encoder and decoder. They can be memoryless. But if you go for 1-to-many mapping, there is a need to introduce memory within the encoder and decoder. Okay. For one particular example that we have taken here is that, see, this one hot coding. In one hot coding, m, the value of m is 2 to the power n. Okay, that means the earlier example we have shown. So that means it is very, it will involve a lot of area increase. But what is the gain that we are getting? So we are introducing redundancy by encoding an n bit word into an m bit word, where m is greater than n before transmission. That we have shown by a small diagram. The 2 to the power n unique data words get mapped to a larger set of 2 to the power m words. In one hot coding, a particular case, an n bit word is encoded for transmission by pressing a 1 on the ith where this is this. Okay, so that means, say, consider I equal to 8. So if n equal to 8, then m equal to 256. Okay, and value of this can vary from 0 to 255. So when the value is say 0101, that means binary 5. So it means that out of the 256 words, only the 5th word will have logic 1. The rest are in logic 0. Okay. Suppose the binary word is such that 1010. So it means that of the 256 words, only the 10th wire will be in logic 1, the remaining will be logic 0. So what is the gain we are getting? The gain is that when there is a change of value, obviously all the inputs cannot be of the same value. So when there is a change of value, there is at most a it ensures that only 1 0 to 1 and 1 to 0 bit transition occurs. That means the power consumed, see that whenever transition is occurring, whenever a capacitance is switched, the bit line capacitance is switched, then only power is consumed. Okay? So that means the power that is involved is very small. Okay? In one-hot coding, the power that is conserved is very spectacular. But what is the downside? Downside is that so many wires are involved. Okay? So huge hardware increase is called for. So this is an extreme case. Now, if you go for another example, say gray code. Gray code has been found very useful for when the data is sent over a bus are sequential and highly correlated. Signal correlations, if we can ensure, definitely there is a scope for power reduction. Okay, that is the main thing. So here you see, the gray code sequence is a set of numbers in which the adjacent numbers have only 1 bit difference. For example, the 8 decimal numbers are there, which are I've just written. Most of you know. So that means if you go sequentially, if you go from say 1 to 2, there is a single change. Okay. If you go say 2 to 3, sorry, these are binary number. The corresponding gray code, if you go say 1 to 2, only single bit change, and so on. So when you have an instruction sequence and the addresses are given by gray code. Okay, so if the instructions are obtained in a straight line sequence, then the power consumed for address line capacity for address line switching is minimum. Only 1 bit change is there. But on the other hand, if you have the binary, say you just take a simple example, you go from 7 to 8, all the 4 bits are switching. Okay, 0 1 1 1 to 1 0 0 sequentially. See, all the 4 bits need to be switched, and 4 times more power will be consumed compared to the gray code. And if you increase the value of n, the gain is very much tangible. Okay, so gray code is useful when you have got sequential access of data. But of course, the branches will be there, and there some violations will be there. Okay, because branches cannot be avoided. And for the data access, it is not possible to have good amount of power, because successive data will be definitely unpredictable and random. So whether you take binary representation or gray code representation, we cannot predict that gray code will give us good result as far as power reduction is concerned. Now come to this data form for arithmetic. Again, through an example, we're trying to show, take the example of correlation. Again, correlation means that we are involved with summation of different numbers. Now, the numbers, suppose that different 4-bit numbers are coming, they can be positive or negative, okay, and say 1024 of them are added up. Now, 1024 means, say, this 1024 we have taken artificially, is that 1024 means 2 to the power 10. Okay, now if you add two numbers, definitely there is a overflow of 1 bit. Now 1024 means 2 to the power 10 order of magnitude. So if all the values are say very large value, there should be a scope for 10 bits for containing the overflow. Okay, so that means 10 more bits are required. 4-bit numbers, it can be positive or negative, and 10 bits for overflow. So this accumulator should be a 14-bit accumulator. Okay, and we have got a output register. This is the final accumulator register, and this is the adder. Adder should be 14 bits. So input register, adder, then there is a this is actually taking case of the let us say this is the final output register. Actually this should be called the accumulator, because this is accumulating the sums. Now if the sampling speed is 64 megahertz, we can afford to have the output to be 64 kilohertz. Okay, because this will be switched only 1 by say 1,000 of the speed in which the inputs are coming. But this register should be clocked as the same speed as this input register. Now correlation length is 1024 with values in the range -7 to +7 and an accumulator. Now question is that why we are studying this? We are studying this because this if you think of the 2's complement representation of the data, it is mandatory that the bit 3, that means the sign bit, should be wired to bit 4 to 13. Okay, that means here this 4th bit should be tied up with the higher bit because of the sign extension. Okay, so when the data changes from the positive to negative, all the bits 4 to 13 should be 1, or the data changes from negative to positive, all the bits 4 to 13 should be 0. Okay, so the higher order, the bit 3 is tied to bits 4 to 13 of adder input for sign extension. Whenever input changes in, the MSB changes, which makes all the 10 orders switch. So that costs some power, sizable power. For uniformly distributed units, sign extension bits 3 to 13 have transition probability close to 0.5 because there is no bias in the values. The successive values that are coming in random, if you take one operand can be positive, the next operand can be negative or positive. So 0.5 probability we are choosing. And accumulator, however, it is a low pass filter. As you think of the low pass filter operation, it is always a constant continuous summation. Okay, the difference happens for a high pass filter. So is low pass filter being accumulator, its transition probability is much less. But the adder output means this adder. Here you will have lot of switching activity. Okay, whenever the input is changing from positive to negative, right? So the question is that this is where we are drawn into. So considering the signal statistics for 2's complement implementation of the accumulator data path, we see that the inputs values beyond 3, it is constant at 0.5 because of the sign extension. Current sum, it is the output of the accumulator. Here the accumulator, it is acts like a low pass filter. So in the higher bits, the switching activity is very small, if not 0. Okay, because once it will start to go through a constant value. Okay, so higher bits, the switching activity is limited, but adder output, here sizable transition activity is observed, and hence it calls for some sizable amount of power. Now the question is, this 2's complement operation, see the trade-off, 2's complement operation, if you adopt, then power consumed is much. But as far as the operation is concerned, the hardware design, that is simple. Whether you do positive number or negative number, you require a single data path. Okay, a single data path is there. Now if you go, see, in order to reduce the power, we can take up sign magnitude representation. Sign magnitude representation means the MSB is sign. Okay, and it is 1 if the number is negative, if it is 0 if the number is positive. However, the hardware design is quite complicated, you see. Complicated means 2 times it calls for replication of units. One is the input register, get it, then the adder, different adders are there, different output registers are there. Finally, it calls for an accumulator here and here. All the negative numbers are added together, all the positive numbers are added together, then finally a subtraction, and then you get the result. Okay, so here you see that what is the overhead. You have to introduce, depending on whether the sign bit is 0 or 1, the input will be routed to this path or this data path. So essentially there are 2 separate data paths, one for the summation of the negative numbers, the other for summation of the positive numbers. Okay, so overhead capacitance is quite sizable, but as far as the result is concerned, that is more important. You see that when all the negative numbers are coming here or all the positive numbers are coming here, the adder, this will not be much. That means the sum output, the adder sum output, the transition activity will not be much. So that's what. Latch sign bit of input register generates gated clocks for to enable positive data path or negative data path. After 1024 cycles, positive and negative accumulated values are transferred to separate registers, and a subtract operation is finally called for, but at a lower frequency. Okay, and low power is ensured as there is no sign extension. That is the chief idea, and so the adder has a low switching activity compared to the previous case in the higher order bits. So sign magnitude performs better than 2's complement for rapidly changing input. See, we get this benefit only for power, but as far as the hardware area is concerned, this is sign magnitude is much worse compared to the 2's complement operation. This implementation needs control circuitry overhead capacitors to generate timing signals for latches. This is another source of power, but compared to the overall operation, so we are showing you here. See, for the sign magnitude case, the same happens to show the transition activity that takes place in the adder of the positive data path and the negative data path. It is quite smaller compared to the adder that is involved in the 2's complement case. Okay, so this one is this. Okay, so that means we gain on the side of power, switching power, but on the hardware side, sign magnitude is worse. Okay, and when input changes very slowly, sign magnitude performs worse. This is due to the switching of the overhead capacitance. Okay, now come to address this ordering. This is a very small example, but you see the problem of multiplying a signal with a constant coefficient. You just change the order, the transition activity can make a difference. Consider this multiplication is decomposed into shift add operations using canonical signed digit representation. So if you do that, for this implementation, you see that we choose to just follow this order. Okay, so you add this much smaller number to this number, and again to the result you are adding this again much smaller number. So here sum 1 and sum 2, they have got very similar switching activity. Okay, because this number is sizable. Assume that this number is much larger compared to these two next number. Okay, so here say switching activity is say 0.7, here it will be same 0.7. On the other hand, if you perform this and this, the transition activity, that means if you add these two first, which are very small number, okay, so switching activity is brought down by sizable amount. So this is the first implementation, this is the second implementation. See that lower power in the second implementation compared to, I'm sorry, this should be first underscore 1. The first adder in the IMP2 has small output amplitude and so lower switching activity. So that means as far as lower switching activity is concerned, this will be adaptable. This will be preferable to this one. Okay, as we show the to different implementation, you see that for the second implementation, sum 1, that means here it is quite small compared to this. That's what we are showing. Okay, sum 1, the transition probability is much smaller compared to the sum 2. On the other hand, for this implementation, this is almost same. Whatever is sum 1, because this great number is involved in both the sum. Okay, this is negligible. These two numbers are negligible compared to the first one. So sum 1 at this intermediate output and this final output, the transition probability is almost same. Okay, thus this curve we obtain. So this is made possible by slight reordering of the inputs. Next, you consider this glitch. So glitch means the undesired power outage. Power consumption due to the difference in switching, difference in the input path, you can say. So for example, A, B, C, D are inputs. Let us say they are simultaneously activated. Okay, so in this linear chain with a straightforward implementation, what we see is that this adder will be activated once. This adder will be activated twice. Why? Because C is coming in the very beginning. Whatever be the result is added. Okay, again when this result is available here, C is again activated. On the other hand, this poor fellow, it is having 3 times transition. That means it is activated thrice. First D is activated, then the result of this is coming, then the result of this is percolated. Okay, so it is activated thrice. So the total switching activity, we have to add up the individual switching activities at the 3 nodes. On the other hand, if you try to balance the chain, that means due to finite delay from one block to next, a node can have multiple transitions in a single clock cycle. In the chain, the bottommost adder computes thrice per cycle. Always, here we are showing a length of path is 3. If you have a length of path 10, then the bottommost element will have a transition 10 times per cycle. Okay. But here, if you balance it out, say, assume that you have got, instead of 3, you have got 16 number of such nodes. So if you do a balance, what you call logarithmic chain instead of a linear chain, then you have got a level 4 addition. So that means at worst, at most, a logic element can have 4 times transition per cycle, in contrast to this straightforward chain where it will have 16 number of transitions in the worst case. So the reduced number of transitions will definitely make way for reduced power consumption. Okay. So in the tree, signal paths are balanced and the extra transitions are got rid of. We can get rid of this. Okay. So that's how mostly we shall see that the tree structure is much preferable compared to the linear chain, although they involve same amount of hardware. Now, well, resource sharing, while we are taking into account, we understand that resource sharing means that the same elements can be made use of by different operations. Okay, as extended to in contrast to the direct mapping. In direct mapping approach, there is a one-to-one correspondence between the operations on the signal flow graph and the operator. We shall show by means of an example, and the operators in the final implementation. If there is area constraint or no need of high throughput, we are happy with whatever these repeated operations are allowed, then go for this time multiplexed architecture, because this will save a lot of cost as far as the hardware is concerned. In time multiplexed architecture, multiple operations on a signal flow graph are mapped onto the same functional unit. So which architecture we will go for? If we are, see, this is very interesting. If we are able, if we can afford to spend much for duplication of elements, okay, or say parallel operations instead of time multiplexed architecture, do we gain by power? Do we gain in power? That is the question. Will we have lower switching activity? Yes or no? Resource sharing in time multiplex implementation can destroy signal correlations and increase switching activity. So it can, that means when you try to share, I mean, if you employ a single adder or a single multiplier for performing different additions or different multiplications, it goes without saying, we cannot predict what will be the input in the next way. Case to case, it will differ. So that means the correlation is absolutely untenable. What we have, lot of skips, lot of what you call skew between the successive outputs. By means of an example, let us show that here. Activity, the switching activity is traded off for time multiplexed hardware or bus sharing. See, this will involve 2 different buses. We are showing the case of 2 counters. Imagine that, see, least significant bit will have got transition in every clock cycle, right? And so that means the transition is 1 by 2, and the second least second least bit of the counter will have transition every other clock cycle, right? And so that means what is the number of bus transitions per cycle for this parallel bus? It is 2 multiplied by this series, then this is roughly equal to 4. So that means when you have parallel buses, this will involve definitely more hardware than this case. Here we are showing by means of a 2 counters. You imagine that 10 counters are there or 16 counters are there. Okay, so that means huge amount of wiring interconnection will be called for. So you can question, well, we are spending so much for the hardware. Do we gain? The gain is what? The transition will be same. Say here we are showing 2 into this. In case of 16, we'll have whatever the number of transitions. Okay, 2 multiplied by say sorry, 2 multiplied by 16, whatever. So in the case of 2 counter example, the total transition activity is 4. There's no bus sharing is there, lot of hardware. But if you go for time multiplexing, see that at one point of time we cannot predict. This will have say value 0, this will have value 255. So difference between 0 and 255 is huge. So this way here all the bit lines will have a transition. Here no bit lines will have a transition, right? So there is an absolute random variation. This lot of unpredictable. This is a very what do you call a particular example. It is a dynamic picture. For different counters, it can from time to time this can reach. So skew between counter outputs. Okay, the maximum value is 255 and the least value is 0. So it will vary between 0 and 255. Okay, so a lot of variations are there, and in general this will call for more switching activity. So time multiplexing, although it gives a great saving of hardware, but as far as the power consumption is concerned, it goes haywire. Okay, lot of unnecessary power will be there. But see, basically when we are constant for area, we have to take time multiplexing, right? So one way we gain, the other way we lose. Now, architecture that is used in practice, general purpose processors have low area and energy efficiency. Programmable digital signal processors, this involves normally replication of hardware. So you can have 2 number of multipliers, 2 number of barrel shifter, 2 number of MAC unit, okay, and direct mapping of algorithms into hardware gives efficient architecture. That we shall see just now. Energy efficiency to the order of say 1000 million operations per second per watt is possible. Area efficiency is there. Let us take one example. A simple signal flow graph. Okay, this we are showing. Say it will call for, if you directly map, what do we get? This will be replaced by 2 registers, D flip-flop. We will have 3 multipliers, 2 adders. So for a direct mapping of this is a signal flow graph we are showing. These are the operators: 2 addition operator, 3 multiplication operator, and 2 delay operator. This is a transform domain. Okay, so a 3-tap FR filter, if you have direct mapping, map the operations of each node to functional units. You can obtain maximum parallelism. Use the minimum clock rate and supply voltage to ensure reduced energy per operation. A high level of parallelism allows larger computation rate than uniprocessors without needing higher clock rates. So you will have 3 multipliers, 2 adders, 2 registers. Okay, registers we require because these can be multiple bits in. So for a n-bit word, you will require n-bit register. This will be a sizable cost. But if you go for resource sharing, then you can employ registers will be needed because the delay will be as per the equation. But you can adopt a multiplexer, okay, and use a single multiplier and a single adder. Instead of 2 adders, why don't you use a accumulator? Okay, because these inputs will come at different points of time. Say the equation for this will be, as you know that, say y of n equal to xn multiplied by a0 plus xn minus 1 multiplied by alpha 1 plus xn minus 2 multiplied by alpha 2. Okay, so it is a FR filter, simple FR filter. Now, the transformations to minimize power are, we now come to address those cases where in an automated manner we can reduce the power. These transformations are changes that are done in computational structure while preserving the input-output behavior. To optimize the number and type of computational modules, their interconnection and sequencing of operations. So we want to optimize power dissipation while meeting the throughput. So 2 key approaches are there: reduce the supply voltage by utilizing speed-up transformation and reduce the effective capacitance switched. First, look at this. To reduce the number of control steps so that the slower control clock cycles can be used for a fixed throughput. So this is another example. That means we can reduce the number of control. We can reduce the number of control steps so that slower control clock cycles can be there for a fixed throughput. Now, you see that this is again what we are doing here. The critical path length is 2. Okay, because from here to here, So we go through multiply and then add. Assuming each operation takes 1 control cycle, critical path of this structure is 2. And what we do here is that, can we bring down the critical path length from 2 per cycle? So what we do, replicate this operation. 2 output samples are computed in parallel based on 2 input samples. One is xn minus 1, the other is xn. So what do you get? This. Critical path is 4 here, but 2 samples are processed in parallel. So effective critical path is unchanged. Supply voltage cannot be altered. So you question, is it useless? Then what we do, essentially all the DSP operations are non-terminating. So there is a loop operation, and when you do the unrolling, assume that all the data are present, then you can afford to have all the computation to be performed in parallel. So after loop unrolling and distributivity and constant propagation, the 2 output samples are represented. So here, assume that this data is available, this data is available, okay? And what we do, you do some replication of the multipliers as well as adders. So 3 adders and 3 multipliers. Now what is the critical path? So as the critical path is there, we see that is critical path of 3 for processing 2 samples. So why 3? Because, well, you can see here that 1, 2, 3. So from here 1 register is there, 1, 2, 3, and then another register. So critical path is 3, but 2 samples are there. That means effective critical path is reduced. Earlier, the path of length was 2, but 2 samples were processed. Here, the path of length 3 is there, but 2 samples are processed. So 3 by 2 or 1.5. So power consumption can be decreased because the overall clock cycle, the frequency is reduced. Because we know that C VDD square multiplied, C into VDD square multiplied F. So one thing is the capacitance can vary, but the frequency will be changed. Earlier it was 2, now it is 1.5. Okay. So this type of small change we can do. Then pipelining to reduce the power consumption, pipelining can now be applied to the structure. Critical path is now reduced to 2 cycles. So critical path is same as the original data path. Sampling rate is half the original rate. So if you reduce the sampling rate, this will allow a reduction of the supply voltage and consequent reduction of power in spite of increase in effective capacitance. Effective capacitance will definitely increase because by pipelining, what you have done, you have introduced these 2 flip-flops. Just in comparison to the previous case, 2 additional D-type flip-flops you are introducing. Okay. So essentially it becomes a 2-stage pipeline. And the critical path is now 2. Critical path is same as original path, but the sampling rate is half. Because earlier, if you had to introduce at 2 kilohertz per sample, now we can afford to have 1 kilohertz per sample. Because you have to allow sufficient amount of time for the data to pass to this stage and to this stage. Okay. So effectively, the power is reduced because you are increasing the time and you are decreasing the power supply voltage. This example we have taken, see, Horner's scheme for polynomial multiplication is well known. So if you do this, you see that the number of operations can be reduced. So x square plus ax plus b, here we see that the number of multipliers is 1 less. Okay. So that calls for lower capacitance and hence lower power, because we have to remember the very important equation, C VDD square multiplied by F. Here what we see is that for complex operation, multiplications are substituted with additions. So what we do, we do the, okay, so this is the first implementation and this is another implementation. So what we do, we follow this right side equation. This implementation has lower effective capacitance for longer critical path than, so voltage in this first implementation can be lower. As this has got a, that means basically what we want to do, if we want to have same throughput for this second implementation as well as the first implementation, we see that here the critical path length has gone up because 1, 2, 3 here here it is 1, 2. So this we can have lower voltage for the first implementation, and hence the overall power can be lower for the first implementation. So first implementation will be preferable to the second one if we want to have lower power. Okay. Well, now this operation, what we see here is that it is a simple expression that input is multiplied by this number. Okay. So what we do, this shows right shifting operations. So the input is made a right shift of 4. Here it is made a right shift of 3. Okay. And B, it is done. Now, if we can do some pre-computation, we can save some power. So brute force implementation means that we will require 5 number of shifts, 1, 2, 3, 4, 5, and 3 addition, 1, 2, 3. But if you pre-compute A, so a quick glance will tell us that if you pre-compute A, then add input to the into 2 to the power minus 2, then add it up. So here the total number of shifts get reduced from 5 to 3, okay, and also the number of addition gets reduced. So uses common terms in constants to share some of the shift add operation. The total shift add operations reduce in number. This is how we name it as sub-expression elimination. This is very much popular in compiler design technique, and this has been introduced here. In fact, for filtering operations, this common sub-expression elimination, you can find lot of use if you read a paper on filtering implementation. So we just show a small example. Lastly, we want to discuss about this, that means sometimes an intelligent, observation of the equations involved in operation can lead us to devise an architecture by which we can reduce the power. So one example we have taken is eliminate the unnecessary computation using conservative approximation. To compute a conservative estimate of the exact distortion value for each candidate. Okay. So before we take up that, we need to have an idea of the motion estimation phenomena. Okay. So basically, this is a block matching algorithm in motion estimation architecture. So this is the expression. The distortion between the two blocks, a macro block of size say n may be 16, n may be 8, n may be 4, whatever, and these are the these are the intensity values at this position of the reference block and position of the. In the next lecture, we shall show in details about this operation. But here we see from the point of view of operations mainly. So just take up these two operations. Okay. So there is a double summation involved. Double summation involved, and this is a operation that is there. Basically, what we want to do, we want to find out the difference of the intensity values of different pixels of this block, and many blocks in the previous frame, and so this is what is involved. Now, more importantly, let us come from the mathematical point of view to reduce power consumption. So this is the original expression. A double summation is involved. So assume that n equal to 16. Okay. What we do, remove one summation term from the above. Right? So that means here, from the outer summation, if you make this upper limit to go to n minus 1 rather than n, okay, then this is definitely greater than this, okay, because one summation we have taken out. Now all of us are aware of this triangle inequality. You see that? Modulus of x plus modulus of y is greater than this. Say x can be 5, y can be say 3, minus 3. So x plus 5, 5 minus 3. So modulus of 2, that is 2, whereas 5 plus 3, 7, 8. So 8 is. Now, so what we see, that means just going back here, So this is greater than this, right? So just you see that we have in place of x we have written this, and in place of y we have written this. Okay. Now based on the above, you define a conservative estimate of. That means we have to actually, theoretically we have to calculate this, but as a conservative estimate, this we have d with a cap. So if we can compute this conservative estimate, this will help us in doing away with unnecessary computation. So rewrite the conservative estimate in this form. This is called a partial distortion estimate for the ith row of candidate macro log. By means of a picture we are showing. That means essentially this, in the conservative estimate, this 1, 2, 3, 4, 5, 6, the sum of these 6 pixels, this is involved in the the things that we have left out. Okay, so we have taken out one summation in the final row, the topmost row. If you had it been n instead of n minus 1, then we would have to calculate this 6 row 6 pixels together. Okay, so what we have to do, we can skip the computing the exact distortion function if the partial estimate of this distortion function is found to be greater than equal to this minimum. This is a pre-stored value. That means now what you have to do, instead of doing all the calculations together, what we do, as we go step by step. Okay, so in the previous block we had already calculated this bottommost row, but in the next calculation we have to delete this row and add this row. So what we do, if we add this, only this 6 pixels sum we add and add to the previous pre-calculated value, then this partial estimate, if we find it to be greater than equal to the minimum value, we can skip the calculation of the entire block. So that means here low power is obtained by doing away with the unnecessary calculation. But details discussion will involve a lot involving the motion estimation algorithm and architecture. That will take up in the next discussion. Okay, so basically it suffices to say that at some point of time, whatever operations we do, we have to be on the lookout for some operations which can be done away with, which can be avoided. Okay, so instead of doing the theoretically predicted or theoretically prescribed operation, if we can perform an estimate of some operations, which can be, and that estimate calculation would be much less computation intensive compared to the actual operation that is prescribed by the theoretical calculation. So this is one example, but I think the detailed discussion will take a lot of time.
In submicron technology, the leakage power, that is static power, is more dominant than the switching power what we have discussed.
Well, in static, in deep submicron technology, the switching, you say that leakage power is more dominant.
Yeah.
There are a lot of research going on in reduction of leakage power. Earlier, the switching power or the dynamic component was generally it was a lion's share of the entire power. Nowadays, leakage power is gaining prevalence over switching power. That's what you say.
Yeah.
Okay. For that, lot of other approaches are there. One, I mean, it will mostly in the technology domain. Okay. Say, like in the what do you call in the one is that in the physical design. Say, for example, say between between source and drain, we have the drain diffusion capacitance, the sidewall capacitance, all are there. So normally some modification is done in the simple placement style. That in place of simple placement style, one can go for something called donut appearance. That means the source is kept and it is surrounded all through by the drain. So thereby the drain diffusion capacitance can be got rid of. And again, something is called finger. That means it's like a horseshoe. There is a what do you call the barrier between the source and drain is kept. Okay, that will also serve to reduce the source and drain the drain diffusion capacity. But a lot of research is going on, but at present I'm not able to.
Okay. The second thing is like short circuit power will not actually comes under dynamic power, but you mentioned it as static power.
Which one?
Short circuit power.
Short circuit power, yes.
Yeah.
Yes, short circuit power is there when the device goes from transition. Say, that means say simple CMOS inverter,
the input signal rises.
Both are simultaneously. One is going from say cutoff to saturation, the other is coming from saturation to cutoff. So for a very small subinterval, both of them simultaneously conduct, and that ensures the.
Yeah, that comes under dynamic power.
Yeah. It actually, as it is involved when there is a transition in the input voltage, so it is you can aptly include in the range of what you call the dynamic.
Dynamic power.
Yes.
It will not come under static.
Or what we can do, let us split it, let us make a partition. One thing we have got a short circuit.
Static power will normally comes under when the input signal is stable.
Static power will be there, or leakage power when the device is not operating at all.
Yeah, correct. The input signal should be stable.
Exactly, you're right.
But here the short circuit power will
here
come
it will be effective when there is a transition in the voltage.
Yeah.
So that will be aptly called
so
dynamic.
it will comes under dynamic.
Yes.
And parallel processing, how latency will comes in parallel processing?
Latency actually in parallel processing.
Because I have a ticket counter, so it is processing 100 people, so it needs 100 unit time. But if I put 4 ticket counters, it can complete in 25 unit time. So there is no chance for latency in parallel processing, correct? Pipelining means I am dividing the ticket counter into 3.
Right.
One is to get the money, one is to allot the ticket, and one is to give the ticket. So there the latency will come, 3 clock cycles. But parallel processing, latency will never come. But you mentioned that.
Yes.
Yes.
Yeah.
And
that is the number of clock cycle. I know that because it is. So if you are having say gated clock, then the next activation will come after a lot of clock cycles. So overall.
No, parallel processing, it is not possible. Like
Yeah,
if you're
it's
having
not
an unique
possible.
processor and multiprocessor.
Because it is the responsibility of the different computing
correct,
units, and they are
correct.
taken to be
So
independent.
latency will not comes in parallel processing. And glitch power, you are using clock gating. So you never mentioned about glitch power. Because clock gating will always introduce a glitch. So that you never mentioned about glitch power in clock gating.
Oh, clock gating I have not mentioned. Right. That is true.
Glitch power. There is a glitch power. That is a one dominant portion of the
critical
dynamic
hazard.
power.
Yes.
You never mentioned about glitch power in clock gating.
Yeah, that means as you distinguish the linear chain propagation of the inputs and the tree structure. So, glitching is less in case of tree. Because glitch means the number of occasions when the switching is
if you are using a clock gating, then definitely there will be a glitch. If the clock is a high frequency clock, then definitely there will be a glitch. So, but that power will be a dominant power.
Yeah, I think for reducing the glitches, one can take the resort to say frequency divider and what do you call down frequency.
Balancing circuit or something else.
Yes,
and loop unrolling or unfolding. So that on.
Oh no, that I am not.
Okay.
Loop unrolling and then folding and unfolding. No. Those transformations.
There is a loop unrolling.
Yeah.
Loop unrolling is actually it is increasing the sampling rate, correct? But so somewhere you mentioned like it is not possible to reduce the total capacitance and you cannot scale down the voltage. But I think we can scale down the voltage if we are doing a 2-level loop unrolling.
Right.
Okay.
Loop unroll, yes.
Okay.
Hello. Sir, in your pipelining architecture, it is possible to compute each and every block operations within a single clock if there may be required the different time. So how do you communicate with one block to another? Means how to correlate with one block to another? Means one block output will be coming into the next step. So if the time is not matched, means asynchronous communications, then what will we do?
In pipelining normally, we have to think of dividing the entire gamut of computations into stages. Okay, and the clock that is sent to the platform register is same clock. We do not send a derived clock to different platform registers. So those and the bottleneck comes from, see, different operations can take different amounts of time. Okay, so for example, say division will take more amount of time than subtraction or addition. So the actual time period of the clock will be determined by the slowest acting computational units. So the pipelining will add up for those cases where the operations take place in sequence, strict sequence, right? If there is chance of parallel operation, pipelining may not help much. So we go for fully parallel structure. Otherwise, what you have to do, if we can take some complex examples where
any queue operations,
subset of operations can take place hand in hand. So there can be a mixture of parallelism and pipelining.
any queue operations or something like that can be queue means in architecture like 8086 and others microprocessor, we are introduced a queue.
Oh yes, that prefetch queue.
Prefetch queue.
Yeah, exactly. So
that can be done over here.
Yeah, that prefetch queue in 8086 will allow you to prefetch 6 instructions from the
6-byte long queue.
Yes. So that will be helpful. That means what are the stages? Instruction decoding, execution, instruction prefetch. So
fetching data will be stored into the queue, and after that decoding and execution will be done accordingly.
Exactly. So instead of straight line program, that will be very much useful. In case of branches, that pipeline hazard, a control hazard,
right?
So then it will tell upon it will have a bad performance. So you have to flush the queue and then reload it.
Okay.
In parallel processing and pipelining, which one is best? First question is.
No, it is very difficult to say.
Because both are increasing the speed. It is the main objective of parallel processing and pipelining. But compared to parallel processing, the pipelining is minimum number of area. It is the another advantages of pipelining. But it have the more number of latency. Then how can avoid the latency of pipelining stages?
Actually, see, for fully parallel operation, if you want, you have to think of the proper, algorithm at hand that you are dealing with. So, for example, matrix multiplication means you have to think of maybe a mixture of pipelining and parallelism, because you have to, for the left matrix, you have to take the entire row and the one column of the second matrix. Okay, so prefetching of the column elements, storing it in a particular register, okay, and then getting them down. So for those operations, systolic architecture may be useful. So which is a systolic architecture means that pipelining is there and partly parallel is also there. But simple operation like say matrix addition, for them pure parallelism will work. So depending on the application, we have to think of either straightforward parallelism or a mixture of pipelining and parallelism. And pipelining will be applicable to even a scalar operation where you are involved with a sequence of dissimilar operations. Okay, so if you are constant, see, parallelism, fully parallelism is applicable only when you have got say similar operations involved repeatedly. But if you have got say particularly when we are trying to use with say transcendental operations, that means trigonometry, hyper trigonometry, and whatever means different operations, or say fraction, division. So when dissimilar operations involve, normally people adopt pipelining. And fully parallelism is strictly purely parallel, that when the same operations are repeatedly involved. Say in case of FIR filter operations, just you multiply and sum. For that you can go with parallelism.
My PG result, my PG project is one of the equalizer where I use the 8-tab FIR filter.
8-tab FIR filter?
8-tab FIR filter in the 16-bit combinations. The input data is 16-bit.
Okay.
That's why I am asking. And also in pipelining, 3 different pipelines, the synchronous, asynchronous and wave pipelining. I choosing the wave pipelining. The clock skew is the major issue. How can you avoid the clock skew?
That wave pipeline you are talking about.
I take the wave pipelining. The choosing the clock skew is very difficult. Any other techniques to choose the clock skew in appropriate range?
I'm not aware. That clock skew analysis not much done actually.
Okay. Common sub-expression elimination method.
Oh, yeah, common sub-expression, right, yes.
How the operation is the decreasing 4 and if A is multiply with 0, 0 or the value is 3. Can you explain the operations?
Exactly. So that means, say 2 different operations are involved with, and say, let us take another, say y equal to ax plus bx squared plus c. So x into a plus bx, or whatever is involved. And another operation there where say z equal to c into bx plus c plus d. So this bx plus c is involved in both y and z. So what we can do, you can just compute one time and reuse it. Instead of, say, if you do straightforwardly, oblivious of the fact that y involves some same common subexpression that is involved in x as well, z as well, so you have to do it twice. But here you do once and then reuse it.
I have one question regarding this voltage supply scaling. Sir, we started from 5 volts supply voltage for diesel ICs and we are coming down to 1. So what is the relationship? Is it done at random basis or there is some logic behind it?
This voltage scaling down?
Supply voltage of ICs.
Yes.
We started with 5 volts. Now I think we are at 1.2 volts.
Oh, yes.
Then it was 2.4 volts. So what is this? Is there a relationship or it is done at random?
As far as I know, is that people take a profile of the power mainly. What is that called? That lambda, that is feature size. So feature size or the line width, when it was say 250 micrometer or say even larger, then normally power supply of 5 volt was used. Then it came down say to 180 nanometer or so. Okay, then the power supply came down to 1.8 volt. Now, why the power supply is brought down? Because with the scaling down of device, unless you scale down the voltage, if the previously used higher voltage is continued to use, then the danger of running into high electric field is there, and consequent second order phenomena like punch through phenomena or that what you call hot carrier or different shorting of the gate and the channel. Those danger is there. To avoid that, the voltage is also scaled down. But these say even now we are talking about say 0.9 volt and the 90 nanometer, or I don't know, even 22 nanometer is made use of. So what is the actual voltage they are using, I do not know. Maybe 0.9 volt or even less, 0.7 volt maybe. The thing is that for one thing, to avoid the danger of second order breakdown phenomena, and another thing is that these scale down devices are mostly used for logic computation. But if you consider, say, you can ask me question that, well, the previous designs use say 5 volt and now we are using 0.9 volt. But different, say, other circuitry like what you call DC to DC converter, then all these buffer circuitry, driver circuitry, all these circuitry are there. So if you continue to make use of them, will you use what you call voltage shifting? But voltage shifting is quite an expensive affair. Say in the boundary you are using 5 volt from our original adapter, but internally the device is operating 0.9 volt. So what to do with them? Rather, what is done is that there is a what you call strict partition of the logic computing circuitry and the input output driver circuitry. So the input output driver circuitry continue to operate at the higher voltage, and the lower, for the lower circuitry, that what you call the voltage scaling down, or rather voltage shifters are employed, so that the computing element, they can take care, say, with the continuous scaling down, the device speed also is going up, and the total computation is completed in a lower amount of time. So lower voltage is ensured for the internal devices, but those devices, they are interested like the what you call the driver circuitry or the what you call the this buffer circuitry. So they are continue to operate in the higher voltage, because for them the design has evolved over long time. So this voltage scaling down is mainly adopted to avoid the second order breakdown phenomena.
Like with voltage scaling, what we do, with voltage scaling, we reduce down the threshold voltage.
Yes, normally we have got what you call constant field scaling or full scaling, and we have got constant voltage scaling. Sorry, constant voltage scaling is called full scaling. So constant field scaling means that the field remains unchanged. So for that, voltage is required to be changed.
Right.
But
the voltage scaling is done, and after that we reduce down threshold voltage. But by reducing threshold voltage, what can happen is switching capacitance can increase. Like for noise, a particular transistor can turn on and turn off immediately. So how that can be avoided?
if you bring down the switching capacitance, sorry, if you bring down the switching, threshold voltage.
Yes.
Yeah, that can lead
But
to
threshold voltage cannot be kept at a constant level. Like if you reduce voltage, VDD, threshold voltage cannot be kept constant. That should be varied. That can be lower down, or it can be kept at higher voltage. But by reducing threshold voltage, how switching capacitance can be avoided? Because transition would be there even for noise, the transistor can turn on.
Right.
So is there any method to avoid this?
That turning on of the capacitance.
Right.
Now, capacitances have also got different components, like say, what you call the oxide-related capacitance and the what you call the diffusion capacitance. The oxide-related capacitance, for them, I don't know very much. Probably something is done on the layout level or something. Like say CGD, then get to body capacitance, get to source capacitance. So those are purely oxide-related capacitance. So they will be affected if you bring down the switching capacitance. Other things are there like source to body and drain to body, which are diffusion capacitance. Okay, so they will be less affected by change of switching voltage as far as I know. So for what do you call CGD and CGS, for them something may be done, like bearing what do you call there are other capacities like what you call fringing capacitance. Okay, then over what do you call side wall capacitance. So for them different techniques are there.